started into basics of semiconductors in the last class, and by this time I am assuming all of you understand what a p-type, what an intrinsic semiconductor is, what an extrinsic semiconductor is, and once you dope a semiconductor, there are two kinds of doping that you can produce. There is a p-type doping, and that doping is caused by who? A trivalent atom. That's caused by a trivalent atom. And there is a n-type doping, which is caused by a pentavalent atom, right? And a p-type semiconductor is replete with holes as majority charge carriers and electrons as minority charge carriers, whereas a n-type semiconductor is replete with electrons as the majority charge carriers and holes as the minority charge carriers. And like I mentioned to you very unequivocally in the last class, that holes behave like positive charges. It's not that the holes move, it's that the electrons hop, giving you an impression that the holes are moving. And the motion of holes is commensurate with what would have transpired to positive charges. Yes or no, right? They would move in the direction of the electric field. Electrons would move opposite to the direction of the electric field if allowed. And then we looked at, once we understood the p-type doping and the n-type doping, out of a single crystal, we created a twofold doping. Part of the crystal was doped as p-type, part of the crystal was doped as n-type, if you remember. And in that kind of a doping, so this was a doping in which this was a p-type and this was a n-type. I have an uncanny knack of writing small n, but typically they use capital N. So not that it matters. So there is, this part is doped as p-type, and it has large number of holes as majority charge carriers and electrons as minority charge carriers, whereas the n-type has a large number of majority charge carriers as electrons and a few minority charge carriers. Does it mean that the p-type is positively charged? No, it's neutral. When you're doping it with a neutral atom, isn't it? And the original material was also silicon crystal, was also neutral. So you've not affected the neutrality. You have just created a redistribution. Same with the n-type. In principle, the whole piece, the whole length would be electrically neutral, right? We are talking of charge carriers as being in majority and in minority. Now, once a p-n crystal was created, what happened? There was a diffusion. Because of difference in concentration levels, there was greater concentration of holes here, and there was a poorer concentration of holes here. And holes migrated from p to n, and electrons migrated from n to p. Because of difference in concentration, That's why it was diffusion. And like we saw in the earlier class I'm assuming I did, that over a period of time, there is a depletion layer produced, right? Say there was a depletion layer produced because holes and electrons killed each other around the junction. There was a depletion layer produced. This was p-type, this was n-type, and there was a depletion layer in which there was an electric field like this. There was a potential barrier, higher to lower potential, and if it was silicon atom, the potential barrier was roughly 0.7 volts if it was a silicon type semiconductor, right? And then once again, there was this p-type semiconductor. There was this n-type, majority charge carriers as electrons, and there was a potential barrier. Designated as follows, right? This was the potential barrier height of the potential barrier, which was 0.7 volts, right? So however, this potential, what did this potential barrier did? It it discouraged passage of holes from this region to this region, right? It discouraged passage of majority charge carriers, electrons from this region to this region, but was favorably disposed towards a drift of minority charge carriers. Minority charge carriers that were electrons here could drift from this region to this region, and minority charge carriers that were holes here could drift favorably in the direction of the electric field from higher to lower potential, right? But eventually there was a situation where the diffusion and the drift annulled. The drift was because of the electric field. Diffusion happens only because of difference in concentration levels. But the important thing is that at some point of time, the diffusion current would cease. Because of this potential barrier, the diffusion current would cease. And for a hole to go from here to here, you would have to energize the hole, right? It would have to overcome this potential barrier of 0.7 volts. Which means now, if you had, so this was my p-n junction and this was my depletion layer. This was the depletion layer, right? Now, see, this is P type, this is N type. Yeah, please come in. There was this depletion region which produced a hurdle or an obstacle, 0.7 volts. And then, there are these minority charge carriers. There are minority charge carriers here, right? And now, if I, and by the way, this p-n junction is commonly designated as with this symbol. This is like, this part is P and this part is N. The symbol for this p-n junction is this Pn, this way. This was the symbolism for, every time you don't have to draw this in electrical circuits, there'll be hundreds of p-n junctions here and there, and you're not going to draw this structure all the time. So this is the symbol used for a p-n junction, right? Now, suppose I connect a battery like this and say there is a rheostat. There is a rheostat here, all right? And I start with a small voltage. Smaller than 0.7 volts, right? Slowly and slowly, what would happen is, if I go on increasing the voltage using the rheostat, this depletion region will start to shrink. Because this, adds potential to this, decreases potential of this. That means the potential difference decreases. The potential barrier is going to shrink. Right? The depletion layer starts to shrink as I go on increasing the voltage using this rheostat. Do you understand why the potential barrier decreases? No. Don't understand, no? See? This point is 0.7 volts higher than this, right? That's my depletion layer. Now, when I connect this part to a higher potential, then the potential difference between these two will decrease, isn't it? Because, right? Say this was x minus 0.7. Or say this was x and this was x plus 0.7 volts, right? Now if I increase this, which happens if I connect it to a positive terminal of the battery, then this potential barrier will decrease. This depletion layer will start to shrink. As I increase the voltage of the battery, the depletion layer will start to shrink. Yes or no? But, essentially to promote a hole to migrate from this region to this region, you must energize it enough so that it can go to a higher potential of 0.7 volts higher than this region, right? That is what you must be able to do. So, eventually, when this goes from 0 to 0.7 volts, it's only shrinking of the depletion layer. But I'm not able to overcome this barrier. As long as this is less than 0.7 volts. I'm not able to overcome this barrier. And there will be no current. There would be no diffusion current. Diffusion would be opposed by an electric field from this region to this region. Right? The moment this battery becomes 0.7 volts, the moment this becomes 0.7 volts, where I'm connecting the p-type to the positive terminal of the battery, the n-type to the negative terminal of the battery, right? So the moment this becomes 0.7 volts, the depletion layer dissolves. The depletion layer dissolves. The holes here would be energetic enough to get passed on to the n-type, right? And diffusion will start happening again. Diffusion will start happening again. So what would happen? The moment this becomes 0.7, this is what happens. The depletion layer vanishes, right? The moment this becomes 0.7 volts, and this is 0.7 for silicon, so it depends on what semiconductor I'm using in principle. So when this is 0.7, the depletion layer that you saw there vanished. The depletion layer vanished. It shrunk to 0, right? The holes here had enough energy to get passed on to the n-type. Right now? Clear now? So now I have, say, holes here. And minority charge carriers electrons here. And by the way, you know, I must have a metallic contact here. There must be this metallic contact. So make sure you write this, put up this metallic contact here and put up a metallic contact here as well. These are metallic contacts at the ends that I'm joining. The depletion layer has gone into oblivion. Do you see that? Moment this becomes 0.7 volts, the depletion layer vanishes, and in the n-type I have these. This is what happens, right? And now, the moment the applied voltage is 0.7 volts with the p-type connected to the positive terminal of the battery, with the n-type connected to the negative terminal. That's important. P-type connected to the positive terminal, n-type connected to the negative terminal of the battery. Depletion layer has vanished, and now there is a rampant flow, rampant diffusion of majority charge carriers. Majority charge carriers are holes here, and majority charge carriers are electrons here. So now there is a rampant motion, diffusion. That's not because of the electric field. Realize diffusion is only because of difference in concentration levels. Think of it not as an electrical phenomena, think of it as a mechanical phenomena. Diffusion is a mechanical phenomena, right? So please understand the difference. When you saw drift of minority charge carriers earlier, that's an electrical phenomena. That happens because of the electric field, right? But when you see diffusion, diffusion should be looked upon equivalently, not really as a electrical phenomena, but as a mechanical phenomena, right? So then, diffusion starts because large number of holes here and meager number of holes there. Large number of electrons here, meager number of electrons there. Yes or no? Now diffusion starts. Holes start to go from P to N, electrons start to go from N to P, right? So then, the diffusion current, and by the way, let me tell you, this diffusion current is of the order of a milliamps, is of the typically of the order of milliamps. You know, in semiconductor devices, you don't encounter currents of the order of amps, etc. Amp is a very big unit. You're talking in devices, we are talking milliamps and microamps. Okay, so the diffusion current, many milliamps. What really happens is when I used a rheostat, when the voltage here was 0, then you know the depletion layer was fat and bulky, and it prevented migration, diffusion of holes and electrons on either side. Majority charge carriers, what does the depletion layer do? The depletion layer prevents motion of diffusion of majority charge carriers, but it can enable small amounts of current of minority charge carriers, which is a drift current, right? But so voltage. So essentially what really happens is, you know, current is very minimalistic, moment the voltage, applied voltage becomes 0.7 volts. This is what happens. There is a sudden surge of current. There is a sudden surge of current. There is rampant diffusion on either side. There is rampant diffusion of majority charge carriers when the applied voltage becomes 0.7 volts, right? This voltage, sometimes they call it a cut-in voltage. They call it a cut-in voltage. They call it a cut-in voltage. Now, the important thing you might, and you would be tempted to ask me this or not, if not ask me this, think about it. See, at cut-in voltage, the depletion layer has vanished. At cut-in voltage, the depletion layer has vanished. And diffusion starts to take place. Rampant diffusion starts to take place. Holes from p-type to n-type and electrons from n-type to p-type, constituting a sizable current in the electrical circuit, right? Now, would you then want to believe that since holes are migrating here and electrons are migrating there, the difference in concentration is decreasing? Because now there are more holes here, some holes come here, and the difference in concentration of holes will decrease. There are more electrons here, few electrons here. Now if electrons go there, the difference in concentration of electrons will decrease. And eventually, when the concentration levels on either side are equalized, you would want to believe that there would be no current. Right? That's at least your initial belief. Right? When the concentrations on either side get equalized, if it's because of diffusion, and if concentration on either side gets equalized, then diffusion current will stop. You might want to think that. Yes or no? Have you understood what I'm asking? This is not something that I'm suggesting. All right. This is what you would want to believe, that eventually concentration levels will get equalized and diffusion current would cease. No. The mechanism is slightly different. Slightly different mechanism here. What really happens is, when the cut-in voltage is reached, like I said, there is a rampant flow, there is a diffusion current starts, sizable magnitude, and you are able to achieve a task. Now, when, let's say, there is a hole. Look at the trajectory of a hole which is part of a diffusion current. Look at the trajectory of a hole which is part of a diffusion current. Say, let me look at this hole. All right. Now, this hole makes its way past this line, enters the n-type, this hole enters the n-type because of this diffusion current, for example, right? Now it starts to swim in this n-type. It starts to swim in this n-type. This n-type is full of electrons. This n-type is full of electrons, yes or no? And how much will this hole escape? How much is this hole going to escape the wrath of n-type? Eventually what would happen is, even before it can reach the end, even if the hole starts to swim randomly in this region, n-type, right? And even before it can reach here, this hole somewhere down the line will get consumed by an electron. Right? An electron can kill a hole, right? An electron can recombine with a hole and the electron-hole pair gets killed. Yes or no? You know, which means even though a hole has gone there, well before reaching the right end, it gets destroyed. You know what I'm saying? So one thing you might want, so the fact that, you know, the concentration of holes here is growing is a myth. Because the hole, it comes here into this region, but it's recombining with an electron because there is such a huge population of electrons here. one or the other electron will consume the whole. One or the electron will consume the whole. There would be annihilation of the whole, right? And therefore, the increased concentration of the whole that you are perceiving here is nothing more than a figment of your imagination. That far and no further, right? Which means believing that the concentration levels are getting towards the point of equalization is not true. It's not increasing the concentration of holes in this region. Despite the diffusion current, the concentration of holes in this region is not increasing. Now, let's say some fortunate hole somehow makes it to the end, survives the wrath of these electrons, this ocean of electrons, it survives this entire cloud of electrons and is able to reach the very end of this region, right? So it's able to reach this metallic end. What happens? Hey, once it comes in contact with this metallic end, the metal has large number of electrons, right? The metal is characterized by a large number of free electrons. And the free electron, which is in this region, will readily be pulled by this hole. Isn't it? An electron will be readily pulled by this hole, and the hole will again get destroyed. Most holes will get destroyed well before reaching the right end. And some lucky hole, if it reaches there, will get destroyed by an electron which is going to pull from the metallic end. Yes or no? Right? So this hole also gets destroyed. So what is it that you see? So what really happens? Okay, now the other thing is, so it's pulled an electron from here, from this, right? So an electron pulled from this metallic end would mean there is an electron that would be pulled from this wire. There would be another electron that will be pulled from this wire. There would be another electron. So there is a flow of electrons that is taking place in this direction. There is flow of electrons that has commenced in this direction. Yes or no? There is a flow of electron that has got initiated, right? There is a flow of electrons that has started with this hole pulling an electron from the metallic end, right? Now. So an electron has been pulled away from here, right? An electron has been pulled away from here, and that means eventually if these electrons, so an electron has been pulled away from this region, right? From this region an electron has been pulled. That means there is creation of a hole here. Yes or no? That means there would be creation of a hole there. Do you then want to believe that the difference in concentration levels will be nearly maintained? Yes or no? And the diffusion current is not going to die out. The diffusion current, far from a common belief, the diffusion current will not die out because difference in concentration levels will be maintained. Difference in concentration levels will be maintained. Most holes before reaching the right end will get consumed by one member of the sea of electrons. And if one fellow out of a few million is able to reach this end, and then there would be an electronic current that would start, and then eventually there would be a creation of a hole. So a hole lost here, which means there is a hole created here. Yes or no?
But sir, eventually it will die out because
No, eventually diffusion current will not stop, because a hole, this region will still be higher in concentration of holes compared to this region. One thing that you would want to then believe is this portion, this part, the right end, has minimum number of holes here, right? Has minimum number of holes here, maximum number of electrons, right? Same with electrons. So when electrons go from N to P, being promoted by the battery to overcome the potential barrier, diffusion, they're not promoted by the battery. It's just that the battery is helping them overcome that barrier. But flow is taking place only because of diffusion, difference in concentration levels, that far and no further. So these electrons will come down here. Now these electrons, they are surrounded by majority of holes, and these electrons will get consumed. So again, the difference in concentration levels of electrons in this region and this region would be reasonably maintained. And if some electron moves to this region, then a new electron will be created in this region. It'll get consumed by a hole, it'll pull up a hole, let's say, it'll eventually, the hole and the electron concentrations in the two regions, the difference is going to be preserved, not killing the diffusion current, not killing the diffusion current, right? And this kind of an arrangement, where I'm just about applying a voltage where the P type is connected to the positive terminal of the battery, P type connected to the positive terminal, N type connected to the negative terminal of the battery, there would be a flow of diffusion current through the circuit. There would be a flow of diffusion current through the circuit the moment you touch the cut-in voltage of the applied voltage. Moment it touches the cut-in voltage, this is what would happen. And the important thing is this kind of an arrangement has allowed flow of current from P to N, right? Flow of current is from P to N. When P is connected to the positive terminal, N is connected to the negative terminal, depletion layer depletes. Depletion layer depletes, gets all finished, right? And there is diffusion current that persists. Of the order of a few milliamps is the diffusion current. And this kind of an arrangement is called a forward bias arrangement. It's called a forward bias arrangement. Forward bias arrangement. And in this forward bias arrangement, if this applied voltage is less than 0.7 volts, there would be no current. Current will get initiated the moment a cut-in voltage of 0.7 volts is reached. But before that, there would be no flow of current. Before that, there would be no flow of current. So there is a regulatory mechanism that gets built into the system. There is a regulatory mechanism that gets built into the system. You apply a voltage less than which doesn't happen in conductors. In conductors, well, even if you apply 10 to the power minus 3 volts, there is going to be a perceived current. But in this arrangement, anything lower than 0.7 volts, lower than this cut-in voltage, you would not perceive any current. Where P type is connected to the positive terminal, N type connected to the negative terminal, that arrangement is called a forward bias. That arrangement is called a forward bias. And so with this symbolism, the forward bias will look like this. This is treated as the P type. This is N type. This is my cut-in voltage that I have applied, or this is the battery. This is how I connect the battery. The P type connected to the positive terminal, the N type connected to the negative terminal of the battery. There is going to be a flow in this direction. Moment this reaches a cut-in voltage. Lower than the cut-in voltage, there is going to be no current. This means the current is flowing from P to N. It means the current is flowing from P to N. This is what it means. But will not flow for applied voltages less than cut-in voltage, right? And this arrangement is a forward bias arrangement, So forward bias may, I repeat, P connected to the positive terminal of the battery, N connected to the negative terminal. Diffusion current takes place from P to N. Clear? Okay. Now, can I wipe this off? And this is roughly the variation of diffusion current with applied voltage. This is my cut-in voltage. Clear? Now, can I wipe this off? See, current is I equal to NEAVD. N will not increase beyond a point, right? So there is a limit. Well, let me tell you what happens. They are anyways minority charge carriers, and they have a limit. They are minority charge carriers. N is very small for minority charge carriers. They have a limit, right? and obviously, the variation is very contrary to what a linear behavior is, right? It's non-linear. I versus V is non-linear here. It's a non-ohmic behavior. Current versus voltage, right? Now, let me take another arrangement. This was my depletion layer. This is P type. This is N type. This was the depletion layer, by the way. In a typical PN junction. And you know, this formation of depletion layer starts the moment the junction is created, and it builds to this a certain value. Now what I do is I reverse the terminals of the battery. I reverse the terminals of the battery. In the earlier forward bias, what did I do? I connected the P type to the positive terminal of the battery. I connected the N type to the negative terminal of the battery. This is what I did. Now I'm going to reverse that connection. What I do is I connect the N type to the positive terminal and the P type to the negative terminal. P type, majority charge carriers holes, minority charge carriers electrons. N type, majority charge carriers electrons and minority charge carriers holes. Now I do this. Where N type is connected to the positive terminal of the battery, P type connected to the negative terminal of the battery, right? Now this positive terminal will start to pull these electrons towards itself, right? Therefore there will be more and more positive layers developed here, right? These electrons, for example, will start to get pulled towards the positive terminal of the battery, will get attracted to the positive terminal of the battery, right? So this region will shift to the right. This positive layer will shift to the right, yes or no? Look at these holes. These holes which behave like positive charge carriers, they will get attracted towards the negative terminal of the battery, right? Therefore, they will create more negativity here, and this junction of the layer will move to the left, yes or no? That means now the depletion layer starts to grow. There is growth of depletion layer, right? In this, depletion layer grows. When the N type is connected to the positive terminal and the P type is connected to the negative terminal. Now, eventually you will find that this becomes my depletion layer. The depletion layer will grow. This is growth of depletion layer, right? And this is what this was my P type, this was my N type. N type this time connected to the positive terminal, P type connected to the negative terminal. Would you then want to believe that diffusion will be further discouraged when the PN junction was formed, right? Because now there is a stronger electric field in this direction. An electric field in this direction would prevent holes from going there, would prevent electrons from coming here, yes or no? Holes can't move all by themselves against the electric field because they behave like positive charge carriers. Electrons can't move by themselves in the direction of the electric field. They would move opposite to the direction of the electric field, right? So that means now Majority charge carriers are discouraged. Diffusion current, not there. Diffusion current, not there. Essentially, you would then want to think that there is no current. There is no current. But what happens is, the electric field is like this, from N to P. The electric field is from N to P. In this direction, what can move? Holes. In this direction, what can move? Electrons. Do I have holes as my minority charge carriers here? So these minority charge carriers in small numbers can move, can drift, not diffuse, they will drift. Majority charge carriers will diffuse, but minority charge carriers will drift. So holes would want to move this way, can move this way, right? Electrons can move this way, right? So now in an opposite direction, from N to P, there is a small amount of current, because see, current is what? Conventionally opposite to flow of electrons. So electrons, which are minority charge carriers here, are going from P to N. So it's as if there is flow of current in the opposite direction, right? So there is a small amount of current. I drift from N to P. There is a small amount of current. I drift from N to P. And this current, that diffusion current was of the order of milliamps, whereas this drift current would be of the order of microamps, 1,000th, right? And why is this very small? Because N, the number of minority charge carriers that are involved, are very small. So you would expect the drift current to be really small, and they are constituted by minority charge carriers. And how does it happen? It goes from N to P. The diffusion current was from P to N, whereas drift current is from N to P, and it's 1,000th of the order of magnitude of diffusion current, right? Very small, right? Now, so current is in an opposite direction this time. So this current is called a reverse current. This current is called a reverse current. This is called a reverse current. See, if those currents were taken as positive, then these currents should be taken as negative, in a direction opposite. Those were from P to N, I took them as positive. This is from N to P, so I take them as, these currents I take as negative. This is called a reverse current. It's called a reverse current. So far so good, right? And this arrangement, in contrast to the earlier arrangement, in the earlier arrangement we had connected P type to the positive terminal, N type to the negative terminal of the battery. There was diffusion current from P to N. Flow of current from P to N was allowed in the earlier type, and that was my FB. FB is forward bias. It allowed current in this direction, right? But when I reverse the terminal of the battery, practically no current. That means almost the current in this direction was zero. That means this arrangement did not allow current from right to left. This is negligible, very small amount of current, so negligible. Then that means in this arrangement is called a reverse bias. This arrangement is called a reverse bias arrangement. This is a reverse bias arrangement in which the N is connected to the positive terminal, P is connected to the negative terminal. With this is wanting to drive a current this way, but cannot. This practically behaves like an insulator. It practically behaves like an insulator. That means in a PN semiconductor, there can be flow of current only from P to N. There can be flow of current only from P to N. So it behaves like a valve. It behaves like a valve. It's a regulatory entity. It's a regulatory element. It regulates. It doesn't allow flow of current from N to P, which is what marks it so differently from a conductor. The conductor has no issues with the direction of the current. You change the polarity of the battery, a conductor will say, all right, who cares? I can permit flow of current in this direction. But a semiconductor will say, no, I will allow flow of current only from P to N. That means you will witness current only if it's forward bias. If it's reverse bias, you will not witness current. It behaves like an insulator. That's why you see this arrow. That means flow of current only in one direction. Do you realize that? It behaves like a valve. It's also called a diode. It's called a diode. A PN junction is also called a diode, a valve. Allowing flow of current only in a forward bias mode. Allowing current only in a forward bias mode. In the reverse bias mode, it will not allow current. This is negligible amount of current. This is negligible amount of current. So this, in this direction, N to P, it says, no, I'm not game for it. I will not allow current. This is negligible, very small. So it behaves like an insulator when it's reverse bias. And even in the forward bias, it applies a clause. It says, hey, all right, I'll permit current from P to N, but provided you have overcome the potential barrier, provided you have reached a cut-in voltage stage. Prior to cut-in voltage stage, I will also offer impediment, I will offer infinite resistance, and you will not be able to overcome that, right? So there is flow in a PN junction. There can be flow of current only in one direction, which is in the forward bias mode. In the reverse bias mode, there would be no current, negligible, right? Now, let me make another remark in this reverse bias mode in which there is a reverse current flowing. Can I remove the clutter from here? So reverse bias is like this. This is my PN. This is my PN. N, this is N, this is P. N connected to the positive terminal, P connected to the negative terminal. This is RB, reverse bias. Arrow means, it's a clear indication that the flow of current is only favored from P to N, not from N to P. Just by changing the polarity of the battery, I will not oblige. Right? Now, just a small remark on this. If you finish copying, let me know. On the reverse bias, so another fact which I wanted to mention, and just to, although I have said that, but exclusively in the forward bias mode, P connected to the positive terminal of the battery, N connected to the negative terminal of the battery, and there is diffusion current from P to N. There is diffusion current from P to N in the forward bias mode. And the reason the current is maintained is because difference in concentration levels are maintained. And why is difference in concentration maintained? Because there is recombination. The moment a hole crosses over to the other side, it recombines with an electron, maintaining the difference in concentration levels. So that current, that you witness in the forward bias is also sometimes called a recombination current, is also called a recombination current. You know what I'm saying? See, had it not been for recombination, that current would have died out. Because eventually the concentrations would have got equalized. If had there been no recombination, the concentrations would have got equalized and the current would have withered away. But because of the recombination, the difference in concentration levels between the P and the N is maintained and there is a continuous flow of current. Right? So it's also called a recombination current. Forward bias current is enabled from P to N only because of recombination. That's the most key thing. Please take cognizance of this, right? It's a recombination current. Had it not been for recombination, the current would have withered away, right? Now, in the reverse bias, where, like I said, N connected to the positive terminal, P connected to the negative terminal, it behaves like an insulator. Practically no current. Practically no current. So what really transpired was, in the forward bias, we saw the current versus applied voltage being something like this. There's a sudden surge of current at cut-in voltage. Right? This is what we saw in forward bias. In reverse bias, since the current is in the opposite direction, it's a reverse current, we take those currents as negative. Right? It's a very small amount of current and That's courtesy, not majority charge carriers, that's courtesy minority charge carriers. NEAVD, N is very small, so you see very small amounts of drift current, which is this reverse current in the reverse bias mode. In fact, what really happens is, if you go on increasing, there is a rheostat and you go on increasing the voltage, right, then, so this is reverse voltage, this voltage is reverse voltage. So if the earlier voltages were positive, then these voltages would be negative, right, they're in the opposite sense, right. What really happens is, a very small amount of drift current flows. I don't remember the values, but this is a very small amount of drift current flows. This is almost, this remains practically constant. This remains practically constant. It's also called a saturation current. This current is also called a saturation current. It reaches a saturation value. As you go on increasing the throttle here, using the rheostat, right, you find that this saturation current reaches a certain value and stays put at that value, reverse current. This reverse current, due to minority charge carriers. Due to minority charge carriers, this is my reverse current. All right. Now, will this keep happening? If I keep increasing this voltage, will this keep happening? No. What really happens is, as I go on increasing this voltage, what I am doing to the electric field here, I am increasing the electric field. I'm increasing the electric field in this region, right? And one more thing that I need to tell you is that essentially, you know, this is courtesy minority charge carriers, and these minority charge carriers will be primarily because of thermal generation of electrons. They'll be primarily because of thermal generation of electrons in the depletion region. Primarily because of thermal generation of electrons in the depletion region. In fact, sometimes when you want to increase the reverse current, what you do is you throw light on this depletion region. When you throw light on this depletion region, there'll be a thermal generation, or you increase the temperature. There would be greater thermal generation of electrons. Don't bother about it. So this is, you know, the reverse bias current. The reverse current is sometimes also called a thermal generation current or a generation current. It's because of thermal generation of electrons. Now, when I go on increasing this, the electric field here increases. But you know, the NEAVD, N is really small, so no matter what, you know, it's about, if there were 5 electrons thermally generated here, then, you know, on increasing the voltage, it's only those 5 electrons that will be mobile. So that limits your current, giving you a saturation current. But when you increase it significantly, when you increase this depletion barrier significantly, when you increase this applied voltage significantly, at a certain value of the applied voltage, say this is V0. There is a certain value of the applied voltage, V0. This is my V0. What happens is, you know, what I have not shown you here are these silicon atoms. There are silicon atoms, right? There are silicon atoms here. The silicon atom that you see covalently bonded with nearby silicon atoms. There are fast moving electrons here. There are very fast moving electrons here now. Because of the increased electric field, there are fast moving electrons here, right? These fast moving electrons, what they do to the crystal is, let's say, look at this silicon arrangement. A fast moving electron can hit this electron. It will knock this electron off place because of its kinetic energy. It will knock off an electron from its covalent arrangement with another silicon atom, say for example, right? So that fast moving electron, why is the electron moving very fast? Because now I have applied a greater electric field. I have applied a greater electric field. So the electrons that are moving this way now have very high kinetic energies, Because of these high kinetic energies, they now start colliding with these electrons. They start now colliding with these electrons present in the covalent bonds, right? So very fast moving electron. See, this was a very fast moving electron, right? And it collided with this atom, collided with this electron, knocked this electron out of place, and this electron was already there. So now I have two electrons, right? And there is a hole created here. Once you knock this electron out of place, there is a hole created here, yes or no? Now I have two electrons. Each electron is capable of producing two more electrons. Each electron now, so this electron can go to some other silicon atom, knock off an electron, and it will produce one more free electron and one more hole. You know? So do you realize suddenly these electrons, because of their rampant motion, fast motion, these fast moving electrons will start to knock off more and more electrons from more and more covalent bonds, creating more and more number of electron hole pairs, And now all of a sudden there is a tremendous surge of charge carriers. And this tremendous surge of charge carriers, good. What would happen is there would be a sudden surge of current. What number of charge carriers now? Because of this, there would be a sudden surge of current. You don't want this to reach, because then it will lose its basic property of not allowing current in the opposite direction, right? You don't want this to happen. So you don't want to apply a voltage all the way to V0. You want to be less than V0 applied voltage, because you don't want this to happen. This is like an avalanche effect. You know what an avalanche is? Right? A small piece of snow that starts to fall and it grows in size. More the merrier. And that's the avalanche effect, right? Here also there is an avalanche effect of electrons. One electron. There was goddamn just one electron. More energy. Hit this. Knock this off. Another electron created. Now each one of them will knock one more electron from some other covalent bond. Will create two more electrons, two more holes. Then each one of them will keep doing the same job. And do you realize there is an uncontrolled growth of electron hole pairs in the process? And now large number of charge carriers. And suddenly I find the current becoming very large at this voltage. And becoming very large, NEAVD. Which means at this voltage there is an avalanche that takes place. This effect is called the avalanche effect. The moment, if effect is felt the moment V equal to V0 in reverse bias. Moment V equal to V0 in reverse bias. Right? And this voltage, when the avalanche takes place, this voltage at which the avalanche takes place is called a breakdown voltage. So as long as you are applying a voltage less than the avalanche voltage, you see practically no current. This saturation current, reverse current is maintained. Moment you cross the limit, a certain limit, moment you reach a breakdown voltage V0, there is an avalanche effect producing an uncontrolled number of electron holes pairs and sudden surge of current in the circuit. Not required, not wanted. The whole purpose gets defeated if you do that, right? So this is so electrical engineers work on this design. They make sure that they operate within V0. In a reverse bias mode, they operate within V0. And you might want to think, why should a semiconductor at all be put in a reverse bias mode? In fact, there are more applications in a reverse bias mode than in a forward bias mode. We'll see that, right? So there is a clear, and this current, like I said, is of the order of microamps. This current is of the order of milliamps, right? So far so good, right? No confusion. Can I wipe this off? Now, see, what we figured out is that a PN junction behaves like a diode, right? This was my PN junction. This is like P, this is N, and it behaves like a diode. Behaves like a diode. It's going to allow current only in the forward bias. If P is connected to the positive terminal, N is connected to the negative terminal. It will not allow current from N to P, right? Now, the other thing is that, you know, most power sources, this power source, for example, you know, when you connect a socket here, this is going to give you sinusoidal voltage. You know, it's written 230 volts, 50 hertz. What does it mean? 230 volts is the RMS voltage, and 50 hertz means, you know, those sinusoidal cycles, 50 cycles per second. 50 times it's changing the polarity. That means if you connect a device here, if you want to charge your battery directly with this, if you want to charge your, let's say, phone battery directly with this, what's going to happen? You know, this is your phone battery. This is your phone battery and you want to charge it. This is the positive terminal, right? What is it that you want to do? How will it get charged? How will a battery get charged? If current flows in this direction, only then it's going to get charged. Yes or no? Only then this battery will get charged, right? If it flows in the opposite direction, it will get discharged, right? So now, if there was no device and I had to directly deploy, I had to take an output from there and connect it to this with the hope and expectation that this is going to get charged. No. So I'm going to get in one half of the cycle. So I versus T is going to be like this. In one half of the cycle, current would flow like this. In the other half of the cycle, the current will flow like this. Isn't it? Will it get charged? It will not get charged. Right? It's what you need is, you need a unidirectional current. This is what you need. Not only that, the voltage that you apply to this, you know, that's 230 volts. You don't want to apply to your battery 230 volts. That's very high. You want to step down that voltage. Now, so essentially, typical power sources are alternating sources, right? And alternating sources are designated as follows. This is an alternating source, right? The polarities, so if this was like 50 cycles per second, 50 hertz, then the polarities change 50 times in a given second. That's what happens. That's not what you need in typical devices, right? You need unidirectional current. So this is not desired across this. This is not what you need, but this is what you're getting from the power source, right? What you need is, say, something like this. Which one unidirectional current, right? Which means, you know, this half of the cycle, you somehow want to flip it over. And get it as this. This half of the cycle, not an issue. This half of the cycle is an issue. You want to flip this over the time axis, right? This is what you want. So you want an arrangement which could do that. You have a question? No? You want current to flow only in one direction. Unidirectional current is what you want, even though your power source is sinusoidal, right? Now, you know, I'm not going to get into the details of that, but there is a device called a transformer. A transformer A transformer has primary windings. These are primary windings. This is the primary coil. And it has secondary windings. This is the secondary coil. This is the secondary coil or secondary windings. And it's, in between, this is the symbol for a transformer. This is the symbol for a transformer. So, based on the ratio of number of coils here to number of coils here, there is going to be a step down. There is going to be a step down voltage, right? But if the input signal here is sinusoidal, the output signal in this is going to be also sinusoidal, although the RMS can be changed. Based on the ratio of number of coils here to the number of windings here, the ratio can be changed. There can be a step down of the voltage, right? Now, typically, there is the first thing when you want to connect it to the power source, you want to step down. Typical devices will not use this voltage. You want to step down. So you use a transformer. This transformer, is connected to the power source. This transformer, the primary windings are connected to the power source, directly connected to the power source. So the voltage across this will be what you get from there. Sinusoidal variation, right? So if it is, this is minus, this is plus 1, there is going to be step down. If because of induction, mutual induction, this will become plus and this will become minus. You're going to get an output signal here. The output signal here would be also sinusoidal. The output signal across the secondary coil will also be sinusoidal, but with, let's say, a lower RMS voltage, However, the frequency will remain the same. If this is 50 hertz, this will also be 50 hertz, but subdued RMS. Now, problem is, obviously, if I had to charge a battery with this, it's not a good idea to charge a battery with this. So in one half of the cycle, this will be plus, this will be minus. And there is that's preferred, that's all right. Current will flow like this and this battery will get charged. But there is another half of the cycle in which this will be plus and this will be minus. And the current will flow like this and the battery will get discharged. Right? That means this arrangement per se is no good. It doesn't give me unidirectional current. Right? The direction of current varies, let's say 50 times in a given second. Bad arrangement, right? So first things first, I want unidirectional current. And how could I achieve a unidirectional current? The step down of the voltage is all right, the primary to secondary, based on the ratio of the number of coils, the step down can take place. But now I don't want a sinusoidal behavior, I want a unidirectional current. At least I don't want the change of direction of the current, right? Now what is done is, say, this is my PN junction diode. This is my PN junction diode. This is plus, this is minus. This is my PN junction diode connected to the secondary coil. And this is my load. This is my load resistance, which could be a battery, for example, in which I want current only to flow in this direction. This is my load resistance. Now notice, so this is my applied voltage, right? And the output is received here. And in the applied voltage, so here also you will see a similar variation. This will be higher potential, this will be lower potential in this part. So current versus time, like this in first half of the cycle. First half of the cycle, this is plus, this is minus, which is the signal received here, That's a signal here in one half of the cycle. Now, in this half of the cycle, say this half, right? What happens is, this is connected to a higher potential, the P type connected to the higher potential, and the N type connected to lower potential. And therefore, do you realize it is forward bias? The circuit is, the diode is forward bias. It's forward bias. So when the current is flowing like this way, anti-clockwise, clockwise, it will allow clockwise current. This diode will allow clockwise current from P to N. This it will permit. And it goes through, right? In the next half of the cycle, when the current was like this, in the next half of the cycle, the voltages changed polarity, plus minus. And there was a proposal for current to go this way. So now, N type connected to the positive terminal, P type connected to the negative terminal. Do you realize now it's RB, reverse bias? And therefore, this current will not be allowed. Reverse bias current will not be allowed. That means there will be no occurrence of the second half of the cycle. So, essentially, what happens is, the way current flows through this is, first half of the cycle allowed, because this is a forward bias, and it can allow currents in this direction, right? First half of the cycle. Second half of the cycle, when the polarities get reversed, this becomes reverse bias. And in reverse bias, there would be no current, because it's not going to allow currents in this direction. In the reverse bias, see, after, this is my input signal. So, when the signal is like this, it's in a reverse bias mode. This circuit is in a reverse bias mode, and it will not allow current. Current will not flow. That means this will go away, right? So this part gone, the dotted part gone. Then we have this part of the cycle. That means again this becomes positive and this becomes negative. That means now there is a proposal for current to flow like this. It will allow this half of the cycle. Then again the next half of the cycle it will disallow. It will allow this, then it will disallow, and so on and so forth. Do you realize that now current is only in one direction? Even though the input signal is sinusoidal, the current through the load is only in one direction, this way. It's not in the opposite direction. Current flows only when this P-N junction in a cycle where it's forward bias. In a cycle in which it's reverse bias, it will disallow current, and this will happen. Then it will allow, then it will disallow, allow, disallow, right? So at least there is a unidirectional current. That is happening through this circuit with this arrangement, right? So the original signal, that was this. The original signal coming to us in the transformer was this. Let's say V versus T, the signal was like this. This was my original signal, right? And now the signal is this. It's only unidirectional. So which means from here to here there has been a rectification. There has been a rectification of the signal, yes or no? But rectified only in half of the full cycle. This was a full cycle. It got rectified only in one half of the cycle, right? One half of the cycle got rectified. And then it got rectified here, but I was idling. This was idling, right? Do you all understand what I'm saying? right? So in one half of the cycle there was rectification, in the other half of the cycle there was idling. Rectification, idling, rectification, idling. Yes or no? This is only 50% efficient. This arrangement is only 50% efficient, but at least it will not allow current in the opposite direction. It will not allow current in the opposite direction. Yes or no? This arrangement is called a half wave rectifier. Is called a half wave rectifier. It's called a half wave rectifier. Yes or no? Do you all understand what I'm saying? But the problem still is, so one, of course, unidirectional current and 50% efficient. This kind of an output, I still can't call it a DC output. I still can't call it a DC output. This output is a pulsating DC, is a pulsating DC. Pulsating half wave rectification. What is this? This is a pulsating DC. And this is pulsating half wave rectification. This is pulsating half wave rectification. Pulsating half wave rectifier. It's a pulsating half wave rectifier. DC में क्या होता है? DC में even the magnitudes don't change with time. No, that's a DC current. यहाँ पे the magnitudes are changing with time, even though direction is maintained. The magnitude. So I can't strictly call it a DC. It's a pulsating DC. I call it a pulsating DC. This is what I refer to this as. And it can be accomplished with one diode in place. With one diode in place. That's a half wave rectification. The problem is that half of any given cycle is unutilized. So it's only 50% in efficiency. This arrangement has 50% efficiency. Yes or no? Right? How to overcome this? Let's see how to overcome this and at least get an output instead of getting an output like this. I would rather, even if it's not a DC, pulsating DC, I want rectification, pulsating DC in every half. I want this, I want this, I want this, I want this, and so on and so forth. This is what I want. This will be obviously preferred over this, isn't it? This is half wave. If I accomplish this, that's a full wave rectification. If I accomplish this, this is going to be a full wave rectification. You know what I'm saying? This is going to be a full wave rectification. So now I'm going to tell you what kind of an arrangement of diodes you could have to accomplish full wave rectification. Got me? Can I wipe this off? Now, so, these polarities will change, say, a certain number of times every second, which is the frequency of the signal, right? This is one diode, and with this one diode, I can only achieve 50% efficiency. Only half of every cycle will get rectified. I want the full cycle to get rectified. How do I do that? What is done is, this coil, the potential gradually decreases from a certain value here to a certain value here. There is a decrease in potential. Do you see that? Along this coil, this is positive, this is negative. So there is a uniform decrease in potential here, right? So if I take a point here, which is generally called the midpoint C of this secondary coil, midpoint C of the secondary coil, it's also called the center tap. It's also called the center tap. C is the center tap. And this is my load. This is my load. This is my load. I do this. And this is my diode D1. And there is another diode that I have, which is D2. This is another diode D2, which is connected like this. center of this coil, it's called a center tap. I take a lead from here and connect it to the load this way. Center tap, it's called a center tap. Now I've created two loops. I've created two loops. There is an upper loop and there is a lower loop. Okay. Now please understand, very simple. So there is one half of the cycle in which this is positive, this is negative. That means P connected to the positive terminal, this will be forward bias. This will be forward bias. Right? If this happens, this is going to be forward bias. Right? Now, between C and this, which is more negative? This is more negative. And P connected to the negative terminal this time, so this will be reverse bias in this arrangement. Do you realize? This is going to be reverse bias in this arrangement. Right? So which means this will disallow current. This will disallow current because it's in a reverse bias mode. This will allow current. In one half of the cycle, this allows current and this disallows. Right? This allows and this disallows. Why this allows? Because this is in the forward bias mode and this is in the reverse bias mode. It will disallow. Right? Good. So one half of the cycle, the signal across the resistance is going to be like this in one half of the cycle. Right? Now, next half of the cycle, what happens? Next half of the cycle, this becomes positive and this becomes negative. That's the next half of the cycle. Do you then realize this P connected to the positive terminal? This will be a forward bias arrangement. This will be a forward bias arrangement. And this connected to the negative terminal, this will be in a reverse bias arrangement. So this diode will disallow, whereas this diode, which is now in a forward bias mode, will allow this. So the second half of the cycle in which the polarities have got changed, the lower diode allows and the upper disallows. And then again there is a rectification. This happens. Unidirectional current across the resistance in both cases. Yes, I will. Look. See, Trishanu, forget all of this. There is a half of the cycle in which this is at a higher potential, this is at a lower potential. Do you then realize this is in a forward bias mode? This is in a reverse bias mode. Yes or no? This is in a forward bias mode and this is in a reverse bias mode. So, under what conditions will a diode allow flow? When it's in a forward bias mode. When will it disallow? When it's in a reverse bias. So, will this diode allow? Will this allow? No. So, which means now there is going to be current through this. So, that's one half of the cycle. Right? Pulsating. The second half of the cycle is when this becomes positive and this becomes negative. So, obviously you realize in this half of the cycle current is flowing through the load only in this direction. Right? Now in the second half of the cycle, where this becomes positive, this becomes negative. Negative connected to the P terminal, so it will be reverse bias, plus connected to P, so this will be forward bias. So which of the two diodes will allow? This diode will allow. So there will be a flow of current like this. But across the resistance there is in both cases flow of current only in the same direction. So this would be my output in the second cycle, this would be my output in the third cycle, and so on and so forth. So the entire wave has been rectified. The entire wave has been rectified with the help of two diodes. That's a full wave rectification. Full wave, obviously pulsating. It's still pulsating, it's still not a DC, it's still not a DC. Right? It's not a DC. It's the midpoint of the secondary coil. Agreed, does not matter. I still have a potential appearing here and here. There will still be a fall. How does it matter? The reverse bias and forward bias arrangements will not get affected. Yeah, so what? From here to here I will still have the same step down. It then gets, look, from here to here I'll still think of it like this. I'll still have a step down and then there will be redistribution of currents. That's all.
That is okay, but how will you take this in central tapping? Is it the midpoint of the secondary winding or something?
No, no, midpoint of the secondary windings only. Through the secondary windings only the electrical arrangement is made. Obviously, no, all these are connected to the secondary windings only because that is where the output is obtained. That is where the output is obtained. So that's a full wave rectifier. But pulsating, still pulsating. Realistically, you know, your adapter, your adapter for charging that you use with your phone, it has two things combined in it. It has a transformer which steps down, and it has a diode which sends signals only in one direction. So it's a, and it doesn't look as big as this really. It's a small cutie thing, and it accomplishes the task. But the key thing is, I'm still getting pulsating. Ideally, I want a direct current through my device. This is my, strictly this is my DC. This is only a pulsating DC. This is what I want. Now, how we get that is a different story, but let me tell you, typically the load resistance that we see here, from where the output is measured, typically I connect a capacitor across this load resistance, and the resistance will, so every pulsating DC has a direct output, direct current component and an alternating current component. But don't bother about it. I will leave that bit of how to filter out the pulsations that you see here, how to filter out using this capacitor is a bypass capacitor, how it can allow only a direct current and will disallow alternating pulsating current. But that's not part of our current curriculum. Those of you who go on to study engineering you will see that more of it in your electrical engineering basic E-Tech courses in engineering. I will not get into how that is accomplished. As long as you understand what a full wave rectification is, half wave rectification is, this more or less takes care of a qualitative understanding of semiconductors. This really takes care of our basic things that we need to know on semiconductor devices. The full wave, the half wave, how a p-n junction operates, depletion layer, majority charge carriers, minority charge carriers, forward bias, reverse bias, and so on and so forth. If you understand all of it, then we are on job.